So in this video playlist, we will go over the topic of AI search or state space search, and we'll formally define the search problem. We will go over certain real-world applications or examples of AI search, and we'll also discuss about certain AI search algorithms. So the first question that one must ask is, what is AI search and who does AI search? So the answer to that is very simple. Intelligent agents perform AI search. Then the next question is, who are these intelligent agents? So these intelligent agents are nothing but your software programs, and these programs can be inside a robot, they can be on a server, they can be in your mobile phone, or they can be anywhere, or essentially anywhere where you can run a software. So these agents essentially run on an abstraction of the real world. So we as software programmers, we essentially abstract the real world and we model it such that it is understandable, and that world becomes the agent's world, into which the agent performs actions. Now let us look at a simple problem, a game essentially. So here the agent's world here is a set of cells. So all these cells are discretized, and each cell can either have food, or it can be blank, or it can also have an agent. Okay, so the goal of the agent is to plan his strategy or plan his trip such that he collects all these food items or eats all these food items without with spending as less amount of effort as possible. So let us simplify this problem first in order to understand the scale of this problem. So let us assume that we have got 3 cells only in this problem. So what are the number of ways in which we can have food in these 3 cells? So so the food can be present in the first cell, it can be present in the second cell only, it can be present in the third cell only, it can be present in the first 2 cells only. So we have got around 2 to the power 3, that is 8 ways of placing food in these 3 cells. Okay. And now if we bring agent into the picture, so if we consider one possibility of food being placed in cells, there are 3 possibilities that the agent can find himself in. So the agent can be in the first cell, it can be in the second cell, or it can be in the third cell. So there are 3 possibilities for the first possibility. Okay. Similarly, there will be around 3 more ways to 3 more ways for the second possibility. Similarly, there will be 3 ways for each of the 8 possibilities, right? And therefore in all there will be 8 into 3, that is 24 possibilities or states. Now if you generalize this problem, we can come across a formula that we've got total number of cells and 2 to the power the cell count. So the total number of cells 3 into 2 to the power 3, that is 8, we will get 24 possibilities. So in this case we have 10 columns and 8 rows. So we've got 80, the total number of cells is 80, which means that we've got 80 into 2 to the power 80, which is equal to 2.6 into 10 to the power 5. So this is the total number of states in the problem. Now let us simplify this problem and just solve the problem of agent trying to find one food item. Okay, so what does the agent do? He can take certain actions. So in this case he chooses to go up, in this case he chooses to go left, in this case he chooses to go up again, and the last action that he performs is to eat the food. Now this is the state of the agent in the end. But remember, the agent may or may not know the position of the food item. Now, if you look at this, here I've only drawn the state space that leads to a goal node. So in this case, the agent started from 6,6. If he went up, he went to 5,6, and then he could have also chosen to go up. He would have chosen to go to left, right, or down. If he chooses to go to left, he comes across this, that is 5,5, then 4,4. The agent can go in either of these nodes as well. You could have also gone here and explored an entirely different tree. Now, ultimately, when the agent is at 4,5, he's found food, and then he can perform the action of eating, and then there's no food in the cell, that is 4,5. So this is a solution that we have found, but finding a solution is not always this easy. I've just walked across all the nodes that would have led me to a solution, but you could entirely go in a direction that is a dead end, right? So AI search basically deals with finding or it is a set of techniques that helps us transverse this tree or the state space graph. Okay. Now, more formally, the state space S can be represented by a set of tuples. So you've got S, which is the set of all the states. So in this case, these will be the nodes in this graph will be the set of states. Then there are actions, and you basically have 5 actions in this example. That is, you could go up, you could go left, you could go right, you could go down, and you could eat. So you've got 5 actions, and not all these actions will be available in every state. So if the agent is present in this state, in this node, he will not be able to take a right, or he will not be able to go down, or he will not be able to eat if there is no food in that cell. So that is a set of actions, but in this case we have all the actions that are possible in any of the states. Then we've got action S. So this corresponds to the set of actions that can be performed when the agent is in state S. So if the agent is in this state, he can go right, he can go left, he can go up, he can go down, but he cannot eat food. Okay. If the agent is in this state, he can do all the 5 actions, which is also represented in the state space graph. So if the agent is at 4,5, he can go up, he can go left, he can go right, he can go bottom, and he can also eat the food. Now what is the result S, A? So that is nothing but after an agent performs an action A in state S, he will be taken to some resultant state, right? Then there's also a cost of performing an action in state S. So we'll come back to this later, but so the agent might incur a cost of moving from one cell to another, right? And as you want to minimize the number of cells that the agent travels, we need to give an incentive to the agent to reduce the number of steps he takes. But you must be wondering why go over this entire state space and scan this graph. you can say that, okay, we can come up with a simple algorithm that this is the agent's location, this is the food's location, and this is 6,6, this is 3,5. I can just subtract the rows of row of the agent, row of the column, row of the food. I can get 3. I can subtract the columns and come up with an algorithm that says that, okay, if I have to take minus dr steps vertically, right? So if it is minus dr, then it is you have to go up, okay? That you have to take 3 steps above, or and you have to take minus dc steps horizontally. That is minus 1 step horizontally. That is, you have to go 1 step left. You could easily come up with an algorithm like that, but this may not work when the world is slightly complex, or in this case also you need to know the location of food, right? If you don't know the location of food, this variable is unknown, right? So this algorithm will not work. This algorithm is perfect for a simple case like this, but it may not work when things get complicated. So ideally, nobody plays simple games. You will have a complex world, and you might have some blockage cells, you can have some harmful cells wherein the agent loses some part of his life, or almost all part of his life. So the agent needs to minimize going in these cells. Okay, so the cost factor that I was talking about here, this can be more prominent here. So we could model the costs here in such a way that if you're going from a harmful cell to a blue cell, you will incur a cost of minus 10. That is, the agent will get 10 rupees or $10 for going from a harmful cell to a non-harmful cell or a safe cell. But if he goes from a safe cell to a harmful cell, he will incur a cost of 10. He has to give 10 rupees. Okay, so he is more likely to avoid going from a safe cell to a harmful cell, and he's more likely to go from a harmful cell to a safe cell. And again, the cost of going from a harmful cell to a blockage has to be infinite, because that action is not allowed. Again, we need to minimize the number of steps that the agent takes. That's why we also incur a cost of transferring from one safe cell to another safe cell, which is 5. So in this way you can model the cost and come up with a solution. Now let us come to a problem that we started initially, that the agent has to plan a trip such that he takes the least number of steps, right? So the agent just I've listed 2 possibilities that the agent can plan his trip in. So the agent can go from start to the food item 2, and he has to take 4 steps, right? From food item 2 to food item 1, he has to take 4 steps, and food item 1 to food item 3, he has to take 7 steps, and he has to take a total of 15 steps in order to accomplish his task. But the agent can also choose a different option. He could go from the start position to food 1, and he'll just take 4 steps. From food 1 to food 2, he'll take 4 steps, and from food 2 to food 3, he will take 5 steps. There is a total of 13 steps. So this is obviously a better solution, right? So this is essentially a search problem within a search problem. The first search problem is to find food items and to find the shortest path to these food items, right? That is the first search problem. The second search problem is to find the shortest path such that the agent is able to eat all these food items. So what you can do is you can pre-compute the shortest path between each of the nodes. You can compute the shortest path from the start to all the food cells. That is, you can create a simple graph such that this is the start node, this is F3, F2, F1, and you've computed the shortest path from S to F1, from F1 to F2, from F2 to F3, and F3 to F4. And then you can start searching the best trip. So in this case, you could, in the first option, you could either take F1, you could go directly to F2, you could go to F3. If you've taken F1, you could go to F2, or you could go to F3 and then go to F2. If you've gone to F1, you could go to F3. So in each step, what you're doing is you're incurring some cost, and the total cost of this trip, that is from F1 to F3 to F2, is going to be a sum of all these edges, the sum of costs incurred at all these edges. So in the next step we will, so in this case this is also another graph that we need to find a solution to, and that is done using AI search techniques. So choosing a AI search algorithm is it depends a lot on the problem that you're trying to solve, and constraints like the memory that you have, the amount of time that you can spend, and the number of solutions that you have in the problem. Also, it depends on the shallowness of the problem, the level at which the solution is likely to be found. So a lot depends on the problem. In the next lecture, we will go over informed and uninformed search strategies.